Let us start now. Oh. So we shall continue the method of finding the eigenvalues of a matrix. Audible now? Oh.
Yes, sir. It's audible.
Right. Yes. So in the last class session, we have seen how to find all the eigenvalues and eigenvectors of a matrix. Now let us recall once again the definition. Any matrix may be given, but it must be a square matrix. Suppose that a square matrix given, let it be A. A be any square matrix of order n. That means it has n rows and n columns. Now take an identity matrix of the same order. Let it be denoted by I. I means identity matrix of the same order. Now obtain an equation in terms of lambda, where lambda is the scalar. How to get means, you see the given matrix A and identity matrix I. You multiply the identity matrix by the scalar lambda. One scalar may be given, it will be lambda, multiplied by lambda. So that in this identity matrix, the diagonal elements are all lambda and all other elements are 0. Now you subtract that matrix from the given matrix and get the determinant. If you obtain determinant, we obtain a polynomial in terms of lambda. That equation obtained, that is called characteristic equation. That means for a matrix A of order n, take another matrix I of the same order, multiply this I by a scalar lambda, then obtain this determinant. That means A minus lambda I is equal to 0. When you subtract the matrix lambda I from the matrix A, only change is that all the elements remain the same because I is the identity matrix. Except diagonal, all the elements are 0. So the same element of the matrix remains except the diagonal elements. All other elements are the same. The diagonal, the elements becomes this diagonal elements minus lambda, because if first element is A11 minus lambda, second element in the second row is A22 minus lambda, like that we get. If you expand it, you get an equation in terms of lambda, that is called characteristic equation. If you solve the characteristic equation, you can find the values of lambda. If it is of order n, there will be n roots for this equation. That n roots obtained, these are called eigenvalues of the matrix, or it's also called characteristic roots, or also called latent roots of the matrix. So latent root, sometimes it's called eigenvalues, or sometimes called characteristic roots. The meaning is same, only get the solution of this polynomial in terms of lambda. That means find the roots of this, that are called eigenvalues. Now, if it is of order n, there will be n eigenvalues. For each eigenvalue lambda, we can find a column matrix X such that when you multiply this matrix A by that column matrix, same answers obtained when you multiply lambda by I. In both cases, you get the same column matrix. If you obtain the same condition, then this column vector X, that is called eigenvector of the matrix lambda, corresponding to the eigenvalue lambda. So for every lambda, there will be an eigenvector. So in order to get it, you have to equate it. If you bring this left hand side, what you get? Ax minus lambda x is equal to 0. Or we can write A minus lambda I into x is equal to 0. That means we get the same type of matrix here. Instead of determinant, we get a matrix. X means there is a vector having n number of elements in that column matrix. Equate to 0. 0 means it's a matrix. All the elements are 0. If by equating, you can find the value of x also. This is called eigenvector. Now we shall take one more example, how to get the eigenvalues and eigenvectors of a matrix. You can find all the eigenvalues and all eigenvectors using this definition. For convenience, take an example. Suppose that is asked to find all eigenvalues and corresponding eigenvectors of this matrix. Here the given matrix, it has 3 rows and 3 columns. The first row, the elements are 2, 0, 1. In the second row, the elements are 0, 2, 0. And the third row, the elements are 1, 0, 2. To find the eigenvalues, all the eigenvalues you have to find. What you have to do is, the solution procedure is like this. First, to obtain the characteristic of this, the characteristic equation of the matrix. Characteristic equation means take this matrix, subtract this diagonal by scalar and equate to 0. So you obtain the characteristic equation. Whenever it's asked you to find the eigenvalues and eigenvector of a matrix, first step is you have to find the eigenvalues. All the eigenvalues you have to find. For that, obtain the characteristic equation. Characteristic equation means the determinant of this matrix minus lambda times the identity matrix is equal to 0. This equation is called characteristic equation. So when it is given like this, no need of showing all the steps. What you can do is, if you get the characteristic equation in this matrix, change is only in the diagonal elements. The rest of the elements remains the same. So this diagonal elements becomes 2 minus lambda. This is 2 minus lambda, 2 minus lambda. Remaining elements remains the same. Instead of matrix, you write this determinant operation and equate to 0. So the characteristic equation becomes 2 minus lambda, the diagonal element you see that this is 2 minus lambda, here 2 minus lambda, this is 2 minus lambda. Remaining elements are same. Equate this determinant equal to 0. Now it is the determinant of 3 by 3 matrix. To get the determinant, you know the process. Any row you select, first row or second row or third row, or any column you select, then you can expand this determinant through that row. Suppose that I take first row. The first row means how to expand the first element into delete the row and column containing that element. If you delete, we get next 2 by 2 matrix. You obtain the determinant of this 2 by 2 matrix. Then after this element, then this element, but alternately plus minus you have to write. First is this is plus 2 minus lambda, then it is minus of this, then it is plus. In this order you have to go. So if you expand it, you know all this method. So 2 minus lambda into, get the determinant of the remaining elements means is 2 minus lambda into 2 minus lambda minus 0 into 0. So we get this term. So 2 minus lambda into this product minus 0. Then this is over. For this element, this sign should be, it is plus, it is minus. So minus 0 into anything is 0. So if you expand, you can write 0 only. It is 0. Then plus this element 1 into, delete the column and row containing this element. So we get this much element. Get the determinant of this 4 element. That is 0 into 0, 0 return minus 2 minus lambda into 1. That is this much is equal to 0. Now we expand it. Here 2 minus lambda is there, and here lambda 2 minus lambda whole square. It is minus 2 minus lambda is there. So from these two terms, 2 minus lambda is common, or expand it. If expand, you get a cubic equation, or you can take here from these two, or this can be written as 2 minus lambda whole square. Here 2 minus lambda is there. You take this as the common factor. You take it outside. What you get again here 2 minus lambda, here minus 1 again. Or as you like, you simplify this. Then again 2 into 2, 4. This minus 2 lambda get, minus lambda into 2, minus 2 lambda plus lambda square get. On simplification, we get this equation is plus 2, and here this one 1, and because of this minus n, it becomes plus. And further simplify, we get a cubic equation of this type. So our aim is to get that polynomial. On simplification, we get this cubic equation. Lambda cube minus 6 lambda square plus lambda lambda minus 6 is equal to 0. Now, characteristic equation is this one. Eigenvalues means roots of this equation. Now you have to get the roots. To find the roots, you can use calculator. It's a cubic equation. You find the roots of this equation using calculator. So when you find it, we observe that you do this work yourself. In calculator, give this coefficient, lambda cube coefficient. For cubic equation, you have to go. That means in calculator, go to the mode. There you press that mode. That it asks whether it is a degree or number of equations. Don't touch that number of equations. You go to this degree. In degree, you press this three degree you press. Then it will ask the coefficient of this variable. First, it will ask A, B, C, D. Feed it all. Finally, press the equal button. It gives the answer. So it gives lambda is equal to 1, 2, 3. But in calculator, first it gives 3, then it gives 1, next it gives 2. But you write in your order. These are the roots. So these roots are the eigenvalues of the matrix. So eigenvalues of this matrix are 1, 2, 3. First step is over. Find the eigenvalues and eigenvectors of the matrix. For each eigenvalue, you have to get the corresponding eigenvector. Eigenvector means a column matrix, but it is since 3 by 3 matrix. In each column, there should be 3 elements. Now, first we shall see what is the eigenvector corresponding to the eigenvalue lambda is equal to 1. All cases you have to consider. One is lambda is equal to 1, when lambda is equal to 2, when lambda is equal to 3. The first case you shall take, case 1, when eigenvalue lambda is equal to 1. Here we have to find eigenvector means a column vector of this type. We assume that let x1, the first eigenvector corresponding to the first eigenvalue, is x1, x2, x3. We assume that this is the eigenvector. If it is the eigenvector, what is the condition to be satisfied? If it is that, then ax1 is equal to lambda x1. There is a condition. If we take left hand side, we get this matrix. What this matrix, that is A minus lambda I into, this will be A minus lambda I into this x1, capital X1 means this column vector, is equal to 0. Right handed 0 means you have to take a column matrix. So it takes 0, 0, 0. So it is A means the given matrix, minus lambda I means change in the diagonal elements only. Remaining elements remains the same. You have seen this one while finding the characteristic equation. Instead of determinant, here you write matrix. Is the difference between characteristic equation and that matrix, this eigenvector. Here, once you write like this, now substitute value of lambda here. Which case here? Lambda is equal to 1. For first eigenvalue, you have to get the values of x1, x2, x3, satisfying these 3 conditions. So, when lambda is equal to 1, what happens this one? 2 minus 1, that is 1. Here 2 minus 1, 1. This is 2 minus 1. All the diagonal elements becomes 1, 1, 1. So this matrix into this eigenvector is equal to 0. So finding the eigenvector corresponding to the eigenvalue lambda is equal to 1 means finding the values of x1, x2, x3 satisfying this system of linear equations. What that system of linear equation is? Multiply these 2 matrices. So that is 1 into x1 plus 0 into x2 plus 1 into x3 equal to 0. That's the first equation. Second equation is second row into this column. We get 0 into x1 plus 1 into x2 plus 0 x3 is equal to 0. Similarly, the third equation you can write easily. That is x1 plus, this is 0. x3 is equal to 0. Second equation is x2 is equal to 0. Third is x1 plus x3 is equal to 0. Solving means it is not, looks very simple, but it has infinite number of solutions. So for that reason, you solve this type of equation by cross multiplication method. Cross multiplication method means out of these equations, there are 3 equations here. You consider only 2 independent equations. From that, by cross multiplication method, we can find one set of solution because it has infinite number of solutions. You find one solution that gives the values of x1, x2, x3. Because for every eigenvalue, there will be infinite number of eigenvectors. Don't think it is unique, right? It will be multiple of that. So one eigenvalue we shall get it. For that, x1 plus x3 is equal to 0, first equation. x2 is equal to 0 is the second equation. Third equation is x1 plus x3 is equal to 0. So these two are the same. So this is the dependent equation. We shall consider only these 2 equations. So considering that 2 independent equations, what again? First equation is this x1 plus x3 is equal to 0. Second equation is x2 is equal to 0. This one you can solve by cross multiplication method. Cross multiplication method means, for convenience, you write all these coefficients of these unknowns in a determinant like this, right? First, the first row, write all the unknowns. Here the unknowns are x1, x2, x3. In the second row, you write the coefficient of these unknowns in the first equation. Now you are considering only two independent equations. Out of these three, we consider only two independent equations. If all three are independent, take two. If only two independent equations, take two independent equations only. Sometimes only one will be there. Then I'll tell what to do. Here, there are three equations. Out of that, one and first and last on the same. So I'll take only two equations. Now write like this. We got the first row of this determinant, right? The unknowns. The second row, coefficient of the first equations. The next row, coefficient of the last equation. Now after that, the value of x1, you write like this: x1 is proportional to, means divided by, delete this row and column containing that element x1 and take the determinant of this. How you get the determinant? 0 into 0 minus 1 into 1. That you write in the denominator. The meaning is that x1 is always multiple of this number, right? Equal to, then x2, you write x2 is equal to, actually in the determinant expansion, this is positive, it is minus, it is positive. So since it's negative, I write minus x2 here, minus x2, delete the column containing that, then these four elements we get. The determinant of this 1 into 0 minus 1 into 0. So this will become 0 is equal to x3 is proportional to, it is delete this row and column. So I get 1 into 1 minus 0 into 0, that is 0. So from this relation, what we identify is that this x1 is always multiple of minus 1. Minus x2 is multiple of this number. X3 is multiple of this one. If you take this each ratio is equal to some k, x1 will be minus 1 into k, x2 will be that 0 into k, x3 will be 1 into k. For different values of k, we get number of eigenvectors, but it will be always multiple of this ratio. So we take only one. So you take x1 is equal to this minus 1, x2 is equal to this 0, x3 is equal to 1. These are taken one eigenvector for this matrix when lambda is equal to 1. Like that, we can find one eigenvector, at least one. It has infinite number. If we equate this ratio is equal to some k, what you get? X1 is equal to minus 1 into k, x2 is equal to 0 into k, x3 is equal to 1 into k. Whatever the value give k, there is an eigenvector. We shall take only this one. So one eigenvector we got, that is first eigenvector when lambda is equal to 1 is x1, x2, x3 is equal to, it is minus 1, 0, 1. Or you can take this is minus k, 0, k. K is equal to 2 means it is minus 2, 0, 2. If you put the k is equal to 3, it is minus 3, 0, 3. Like that, we can write infinite number of eigenvectors for this. So like that, we can get eigenvector for every eigenvalue. So for lambda is equal to 1, you got. Similarly, you shall get another case when lambda is equal to 2. When lambda is equal to 2, assume that x2 will be the eigenvector. So there will be three elements in that column matrix. Instead of x1, x2, x3, you can name it y1, y2, y3 to see the difference from that eigenvector and this eigenvector. We are giving some name, that's all. That is when lambda is equal to 2. If it is the case, if it is the eigenvector, what the condition for that? Then it must satisfy this condition. That means A minus lambda determinant, this matrix A minus lambda into this x2, that must equal to 0. But here lambda is equal to 2. When you put lambda is equal to 2, what happens to this one? All these diagonal elements becomes 2 minus 2, that is 0, 0, 0. So we get this matrix into this column matrix is equal to 0 matrix on the right hand side. Now expand it, 0 into y1 plus 0 into y2 plus 0 into y1 into y3 is equal to 0. So one equation we get this y3 is equal to 0. From the second, all these are 0. So y1 is equal to, sorry, this is y1 is equal to, okay, this is all 0. We can't write anything. Here last equation 1 into y1 is equal to 0. So now y3 is equal to 0, y1 is equal to 0 means don't think 0, 0, 0 is the eigenvector. That is wrong. Here there are two independent equations. What is that? One y3 is equal to 0, another is y1 is equal to 0. So don't think this is the answer here. We have to get two independent equations. So I get take two independent equations. One is y3 is equal to 0, another is y1 is equal to 0. Now Solve this one by cross multiplication method means write the determinant. In the first row, write all the unknowns y1, y2, y3. The coefficient of y3 is here 1, x1, x2, y1, y2 are 0 in the first equation. Second equation, we get this is 1, remaining 0. Now, how to solve by cross multiplication method? Is y1 by, delete this row and column, so 0 minus 0, 0 into 1, 0 get. For the next one, it's minus y2, remove this column and row, then 0 into 0, minus 1 into 1, this is minus 1 you got. Y3 by, this is 0. So if you simplify what you get, y1 by 0, is minus y2 by minus 1 you get, is minus by plus we get, y2 by 0, it is y3 is equal by 0. So this is taken as one eigen value. Actually, if you take this ratio is equal to k, y1 is equal to 0 into k, y2 is equal to 1 into k, y3 is equal to 0. So any value of y2 satisfies this condition. But for y1 and y3 is equal to 0. This is the condition mentioned here. So y3 must be 0 and y1 is equal to 0. The same value get. But y2 can take any value. 1 is one minimum value. So eigenvector corresponding to the eigenvalue lambda is equal to 2 is, you can take 0, 1, 0, or it is 0. Here take any value k, this is 0. So once you know this logic behind this, instead of solving all this, immediately can write y3 0, y1 0, y2 is not there. Y2 is not there means you give any value. 1 is one value only. It may be 2, it may be 100, it may be 300, anything give. These are all eigenvectors. So this is the eigenvector when lambda is equal to 2. Now we shall get one more eigenvector that is corresponding to the eigenvalue lambda is equal to 3. Now assume that x3 is equal to z1, z2, z3 is the eigenvector when lambda is equal to 3. Then the condition is a minus lambda into this x3 must equal to 0. So a minus lambda means same matrix we get, only change in the value of lambda. Here lambda is equal to 3. When lambda is 3, what you get? It is 2 minus 3. It is 2 minus 3. It is 2 minus 3. The diagonal elements will be minus 1, minus 1, minus 1 get. Into this z1, z2, z3 is equal to 0 on the right hand side. Expand this matrix, that is minus 1 into z1 plus 0 into z2 plus 1 into z3 is equal to 0. Second equation is here minus z2 is equal to 0 again. Last one is similarly we get like this. Now take two independent equations. Minus z1 plus z3 is equal to 0. If you multiply this one by minus sign, this becomes z1 minus z3 is equal to 0. That means these two are on the same equations. So we take only these two independent equations. So considering the independent equations, we get minus z1 plus z3 is equal to 0. The last one is the multiple of this, that is dependent. So z2 minus z2 is equal to 0 or z2 is equal to 0 you can take as you like. Now use this cross multiplication method like this. Write the unknowns in the first row, the coefficient of the first equation in the second row, coefficient of the unknowns in the third equation. Here minus 1 only is there. Now by cross multiplication method, z1 by, delete this row and column, so 0 into 0 minus of minus plus 1 we get is equal to, this minus z2 is proportional to, this is 0 and this is 0, and z3 is proportional to plus 1 minus 0. So what is z1 is proportional to 1, z2 is proportional to 0, z3 is proportional to 1. So I take it as one eigenvector x3 corresponding to this is 1, 0, 1. Again, it not be this one, it will be any multiple of this column vector. If you multiply this one by k, it will be k, it is 0, it is k. For any value of k, it is an eigenvector. As I told in the beginning, eigenvalue, for every eigenvalue, there are infinite number of eigenvectors, right? So, but for every eigenvector, there is unique eigenvalue. So that must be noted. So like that, we can get the eigenvalues and eigenvector of a matrix. To get practice, let's do one more example. Suppose this asks you to find all eigenvalues and eigenvectors of this matrix. So now we shall go quite fast because you know now the method, how to get the eigenvalues and eigenvectors. First, you have to get the characteristic equation. Characteristic equation means determinant of a minus lambda is equal to 0. So what to do means in this matrix, change this diagonal elements to that element minus lambda. If you write it and equate to 0, now you have to solve this, expand it. When you expand it, you get minus 2 minus lambda into 1 minus lambda into minus lambda minus 6 into minus 2, this minus becomes minus 12, this plus 12, right? Then minus 2 into, delete this row and column, 2 into minus lambda is minus 2 lambda minus, this is minus 6 into minus 1. So minus or minus plus. So minus plus 6 you write like that, minus, and here this is minus of minus plus 3 you get. There's a mistake here. It is minus, sorry, this is correct. So it is plus, it is plus, it is minus, it is plus, minus 3 only. It's correct. Minus 3. Delete the column and row containing that. 2 into minus 2, minus 4, minus, then this much into minus 1, minus or minus plus 1 you get, is equal to 0. Now simplification. 1 minus lambda into minus lambda means it's minus lambda plus lambda square minus 12 you get, and expand it. If you simplify, finally we get this cubic equation that we can do this work. So first we get one term with the lambda cube, next lambda square minus 21 lambda minus 45 is equal to 0. Rest thing is find the values of lambda using calculator. If you use calculator, feed all this coefficient, we see that the roots are minus 3, 5. But here you have to take care. While using calculator, it gives these two values only, minus 3 and 5. Next, this one is repeating root. That you have to understand. This minus 3 is again repeating. If you use it, it gives the minus 3 and minus 5 only, right? So which is repeating? To get this, you put one value here, substitute which value satisfies twice. For there's a method, you should know which one repeats. Otherwise, in the calculator it gives only two values. There, how to identify which value repeats, that must be known. Once you know this, you can write minus 3, 5. These are the eigen values. Now, for each eigenvalue, you have to get the eigenvector. Since it is repeating, take only one eigenvalue, minus 3. At that, what is the eigenvector? So to get the eigenvector, what is the method? First, check x1 is equal to x1, x2, x3, the eigenvector corresponding to the eigenvalue, lambda is equal to minus 3. Then the same process, this matrix into this much is equal to 0. Lambda is equal to minus 3 means substitute it, minus 2, minus 3. So minus of minus plus 3 you get, minus 2 plus 3 is here 1, and here 1 minus of minus plus 3 here 4 you get. This is 3. Remaining elements as itself. So we get, solve this. If you expand it, we get 3 equations here. But here the interesting is, there are x1 plus 2x2 minus 3x3 is the first equation. Second equation is 2x1 plus 4x2 minus 6x3 is equal to 0. This is nothing but multiple of the first one. If you multiply first equation by 2, we get it. And again, here, if you multiply this one minus 1, we get this equation. So only one independent equation is there. Here, these two are dependent equation. We need at least two independent equations to solve it. So in this case, how to do or how to find the eigenvectors? So for that, first you choose the eigenvectors, independent equation. Only one independent equation is there. So which is that? The first one, right? So next, no independent equation, what to do is, you take any one variable as 0, either x1 0, x2 0, or x3 0. In this case, I'll take x2 is equal to 0. Considering x2 is equal to 0, write this unknowns in the first row. In this equation, what are the unknowns? 1, 2, minus 3 written. Then, if x2 is equal to 0, here, what happens? This coefficient is 1, this coefficient is minus 3. That you are free to select. If you take x1 is equal to 0, we can write this coefficient here 0, it is 2, it is minus 3. If you take this one is equal to 0, I get 1, 2. So depending on the case, we get the eigenvectors. Now, you solve by cross multiplication method. How we done is, I've taken here x2 is equal to 0. Then same method, that cross multiplication method, if you solve it, we get x1 is equal to 3, x2 is equal to 0, x3 is equal to 1. Need not be this answer. If you put x3 is equal to 0, we get another set. If you put x1 is equal to 0, and set, all are correct eigenvectors because it is not unique. So with respect to this condition, this is the one eigenvector. Now similarly find when lambda is equal to 5. Lambda is equal to 5, the same process. What to do means multiply the equal to 0, lambda is equal to 5. If you substitute, you get this matrix. Here, what the change is, here we get 3 independent equations. You may see that no one is dependent here. If 3 independent equations there, you take any 2. consider any two independent equations, right, and solve it. I have taken the first two, right? First one is minus 7x1 plus 2x2 minus 3x3 is equal to 0. Second is 2x1 minus 4x2 minus 6x is equal to 0. Not necessary this one. So only one independent equation is what is done, that you have to note that. If only independent equation is put any variable is 0, get another equation and write that coefficient in that matrix and use cross multiplication method. If three are independent equations, from these three, take any two, either first two or first and last or last two. Here I have taken the first two equations. Then by cross multiplication method, you can solve. What to do? The same process, the variables in the first row, the coefficient of these unknowns of these two equations in the next two rows. Use this cross multiplication method, x1 by that 2 into minus 6 minus 12 minus 3 into minus 4, it is plus 12. So minus 12 minus 12, and minus x2 is proportional to this, and x3 is proportional to minus 7 into minus 4, that is 28 minus 2 into 2, 4. So here minus 24, this 28 minus 4 means 24, there 42 plus 6 is 48. 24 is common throughout. Divide throughout by 24. So we get here x1 by minus 1. This is 3. Here 24. 1 we get. So, or you multiply by minus sign to make it plus. So what you get? x1 by 1 is equal to x2 by 2 is equal to x3 by minus 1. Dividing throughout by minus 24. So this we obtain as the eigenvector. But don't think this is the answer, only one answer. It has infinite number of eigenvectors. So you are free to select any one of the eigenvectors. So I have selected this one by considering these two equations. So what is the eigenvector? x2 is equal to x1, x2, x3 is equal to 1, 2, minus 1. So like that, we can get all eigenvalues and eigenvectors. But while finding eigenvectors, you have to keep in mind that after, for any eigenvalue lambda, get three equations with three unknowns. Which equations you have to consider? Only independent equations you have to consider. If all the three are independent, take any two independent equations using cross multiplication method, get the unknowns. If only two unknowns, no doubt that. Only one means make one more equation by putting any one variable is equal to 0. Then use cross multiplication method. Like that, we can get all eigenvalues and eigenvectors of a matrix. Now, we shall take one more small part here, that's bounds for eigenvalues. There is a theorem. Using the theorem, when a matrix given, we can find what are the bounds, means where these eigenvalues of the matrix lie, right? That will lie inside a circle. That circle you have to identify. For that, there's a theorem, right? So that's written later. So this must be come later. So okay, first I'll tell this theorem. This theorem is called Descartes circle theorem. What this theorem states is that every eigenvalue lambda of an n by n square matrix always satisfy the inequality. This inequality is given by like this: lambda minus a suffix mm is less than or equal to magnitude of am1 plus, this magnitude means absolute value of am2 plus absolute of value of am m minus 1 plus etc. absolute value of amn. So what do you mean by this? When a matrix of this type is given, the elements of this matrix are identified by aij. Any eigenvalue, that means lambda, right? We have to find where it lies, means lambda minus amm. What in by am? Is the diagonal element of mth row. Select any row of this. It may be first row means you write a11, second row means a22, third row means a33. Take any row, let it be mth row. Then this lambda minus that diagonal element, that is amm, always less than or equal to sum of this. What this represent? This is the positive. You have to take the absolute value of the remaining elements. am1 is in that row. What is the remaining elements? Add all this. So this magnitude value will be less than or equal to this value. That's the theorem states. But here lambda minus am means you should know it always represents a circle with the AMM as the center and this sum as the radius. So this theorem states, for that reason it's called circle theorem. Lambda minus AM means there's a circle with the center AM which is less than or equal to this sum, means this sum is the radius of the circle. Inside the radius this eigenvalue lies. That is called Jacob-Green circle theorem. One example let us see, right? So whenever this m is less than or equal to 1, this is the condition. I'll give one example. Suppose that's asked, find the bounds for the eigenvalues of this matrix. For this matrix, you have to get the eigenvalues. So how to get, what are the diagonal elements here? 5 minus 2, 5. So this theorem shares this eigenvalue lies between, for the first row, this one, 5 minus, so this lambda minus 5, the AM means this one, 5 minus A11, this is A11 for the first row, lambda minus this 5 less than or equal to sum of the remaining elements. That means what the in that row remaining elements 0 and 1. So this, using that theorem, what you get this, for the first row condition we get the modulus magnitude of lambda minus 5 less than or equal to, this is the first element, magnitude of this plus magnitude of the second element in this row, but this sum is equal to 1. This is the first condition. For the second one, for this one, lambda minus of minus 2, that means plus 2 less than or equal to, here remaining elements are 0 plus 0, that means is equal to 0. For the last one, 5 minus lambda is less than or equal to, sorry, not 5 minus, lambda minus 5, positive value of this less than or equal to mod 1 plus this 0, that is 1. Now from this equation, what you got, lambda plus 2 less than or equal to 0, this implies lambda plus 2 is equal to minus 2, because here no number is there. So lambda is equal to minus 2 is one eigenvalue for this, right? The rest, the first and last equation one is same. Because of that, other two eigenvalues of this matrix lie or lie within or on the boundary of the circle. Equation circle is nothing but lambda minus 5, that you have to write here. Yeah, lambda minus 5 is less than or equal to 1, because this sum is 1, this also 1. So what this theory states is that when a matrix of this given, that eigenvalues of this matrix lies within the circle. It is a circle with center at 5 and radius is 1. Within the circle, two eigenvalue lie, because the first from this, since the second equation right hand 0, one eigenvalue get it minus 2. Other two eigenvalues, for a 3 by 3 matrix, there should be 3 eigenvalues. Other two eigenvalues lies inside circle. So like that, you can find the boundary for the eigenvalues. So one more example you can try for this. Find the